Tokenizers are the gatekeepers of how artificial intelligence understands text. They take the continuous stream of human language and chop it into discrete units called tokens. Everyone agrees that a good tokenizer should be lossless. This means that if you run the text through the process and then reverse it, you get the exact original input back. No characters missing, no characters added. It sounds like a baseline requirement. It sounds trivial. But is it actually enough to just claim losslessness? Or does the way we handle this compression create hidden costs that matter in real-world applications? There is a recent study from Amazon Web Services AI Labs that challenges how we think about this. They introduced something called meta tokens. The core idea is similar to how file compression works in your operating system. It replaces repeated sequences in the input with unique identifiers. This is analogous to a compression algorithm known as LZ77. The result is that the sequence of tokens becomes shorter. In their tests, they achieved sequence reductions of 27% and 18% across different tasks. This is where the theoretical claim meets the practical reality. If you are running a large language model, shorter sequences matter immensely. The attention mechanism in these models has quadratic complexity. This means that if you cut the input length, the computational cost drops significantly. Their research shows encoding costs reduced by 47% and 33%. This is not just a theoretical win, it is a measurable efficiency gain for production systems. However, we must look at the overhead. The claim is that the transformation is trivially reversible. This preserves all semantic and syntactic information. But there is a catch. A tokenizer cannot be lossless for all inputs without an impractically large vocabulary. This brings us to the trade-off. Current mainstream tokenizers often sacrifice perfect reversibility to achieve better semantic grouping. They group words together to help the model converge faster. The meta-tokens approach suggests that for high-stakes applications where data fidelity is paramount, we might need to revisit this balance. The authors acknowledge a negligible performance gap compared to uncompressed inputs. They argue this is attributable to current model limitations rather than the method itself. They posit that larger models would eliminate these discrepancies entirely. Consider the context of Retrieval-Augmented Generation. This is a pipeline where systems search for information before answering. In these environments, every token counts. If you can compress the retrieval context without losing the nuance of the source text, you save on latency and cost. But there are other approaches. Some researchers discuss hybrid tokenization for specific languages like Turkish. Others propose tokenizer-free architectures. These do not address the specific theoretical properties of lossless tokenization. They focus on language-specific morphology or bypassing tokenization entirely. The consensus emerging from the literature is that while the observation that lossless tokenizers lose nothing and add nothing appears trivial, the meta-token study validates its formalization as a critical advancement. It bridges the gap between theoretical reversibility and practical deployment. Here is the thing that often gets missed in the discussion. Lossless tokenization is a necessary but insufficient condition for optimal tokenizers. The primary challenge lies in vocabulary efficiency and semantic alignment rather than just reversibility. Research indicates that lossless tokenizers often introduce implicit overhead through larger vocabulary sizes or fragmented sequences, contradicting the add-nothing intuition in practice. When you compress text into tokens, you are essentially building a dictionary. If that dictionary grows too large to handle the entropy of the corpus, the system becomes unwieldy. The feasibility of lossless tokenization is strictly dependent on the vocabulary size relative to the corpus entropy. This means a tokenizer cannot be lossless for all inputs without an impractically large vocabulary. Empirical benchmarks show that different lossless tokenization strategies yield significant performance variations in downstream large language model tasks. This suggests that the specific compression method matters more than the lossless property itself. It is not enough to say the data is preserved. You must ensure the preserved data is structured in a way the model can process efficiently. Formalizing the trade-off between losslessness and compression efficiency is critical, as current mainstream tokenizers often sacrifice perfect reversibility to achieve better semantic grouping and model convergence. We are at a point where we can afford to be more rigorous. The quadratic complexity of transformer attention mechanisms yields significant computational savings, reducing encoding costs by 47% and 33%. While the authors acknowledge a negligible performance gap compared to uncompressed inputs, they argue this is attributable to current model limitations rather than the method itself. This work provides strong empirical support for formalizing lossless tokenization as a practical efficiency tool for high-stakes applications where data fidelity is paramount. In production RAG pipelines, the ability to reduce token count inflation without losing semantic meaning is a game changer. It allows for faster response times and lower compute costs. But it requires a shift in how we design the underlying compression layer. We cannot simply assume that lossless means free. We must quantify the computational overhead. We must measure the encoding and decoding cycles. We must understand that while the observation that lossless tokenizers lose nothing and add nothing appears trivial, the metatoken study validates its formalization as a critical advancement for balancing computational efficiency with strict information preservation. This effectively bridges the gap between theoretical reversibility and practical deployment. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.